We're looking forward.
Thank you very much, Andrea, for the kind introduction. And I hope I also have extra time. Excellent. So I'd like to share with you today a story that is in some sense similar, but in other ways very different than what Christian just told you, in the sense of that we're not working with ions, but with ultra-cold atoms. And can I see my slides? No?
It's number one, input number one.
Yeah. Great, thanks. And it's mostly a story about if you want to do something new in quantum science, you actually have to work a bit on technological parts of it as well. You can't get around that, and I'll explain a bit what that means. So we're working with ultra-cold atoms, and why would you want to do that? Generally, these atoms we trap in regular arrays, and we create these regular arrays, these trapping potentials, with laser beams. We can't use ion traps because our atoms don't have charge. The advantage is that generally atoms are fundamentally alike, and that you can buy a lot of them, right? It's very easy to get 10 to the 23 atoms that are exactly the same. They also make very coherent qubits. We can have very long coherence time, and they tend to be very insensitive to the environment if you do it right. One can also make them interact coherently. This can be done either by having them collide with bosonic or fermionic statistics, or these days now also with laser-controlled gates based on very strong Rydberg interactions. Generally, the traps that we can make, they're just limited by how you arrange your laser beam, so they can be very stable, they can be very flexible. Now, I'll show or talk a bit briefly about 3 examples. One is an optical lattice clock that makes use of the atoms that I will be talking about, strontium. It's currently one of the best optical frequency standards there is. One can also make use of these atoms for building quantum simulators, and I'll show a bit about that. And very recently, people have become highly interested in also using these atoms for quantum computers. Now, our experiments are tabletop experiments. You can see this is a photo of my lab. You require a team of people to work on them because in the end, they tend to be kind of complex. But it's still tabletop, so you can still do everything yourself. You don't have to rely on big facilities to do the work. And can you do this with any atoms? In principle, yes, but unfortunately, no. We tend to like to work with 1 electron atoms because of their relatively simple electronic structure. So the prototypical one of these is hydrogen, and with 2 electron atoms, of which the prototypical one is helium. But unless you're really amazing, you can't work with them because all these the main laser transitions that you need to cool these atoms are in the extreme ultraviolet. So most of us tend to work with rubidium, which is slightly heavier, or in my case, with strontium. Now, what's special about these strontium atoms is very similar to what Christian just showed. It has a helium-like structure, so there's singlet states, there's triplet states, and you can have broad cooling transitions for fluorescence detection and initial Doppler cooling, and there are these very narrow intercombination lines, and in strontium that turns out to be a line width on the order of 1 millihertz, leading to lifetimes on the order of 100 seconds. Now, so I'm not going to go into details, but this building a frequency standard on this transition here worked really well in the last decade or so, maybe a bit longer by now. But I'd like to flash real quick, why do you care? Right? Clearly, one can add more digits to a measurement like this, but why? And the answer is that once you have this capability, you can do new things. So here's a very recent measurement from Junier's group where, because now they can interrogate this optical clock transition so precisely, they can measure the gravitational redshift in a sample that is about 1 millimeter tall. And they see a frequency difference between here and here. So that gives you access to a new window on physics, namely gravity at the millimeter scale and below. So that's why one actually cares about making these things better and better. Now, I said that worked quite well, and it opened up a bit of a new field. So because of all the quantum technology associated with these strontium optical lattice clocks, people started using it. And there's all kinds of experiments now ranging from putting these atoms on optical tweezers to building continuous atomic sources that recently just worked. It's a very cool experiment, building atom interferometers, new light sources, and so forth. Now, what about us? What are we doing? So we're a quantum simulation group, and when I joined MPQ, I was interested in combining the technologies from optical lattice clocks, like I was just saying, with the optical lattice technology and quantum simulation strength that the Bloch group in Munich is known for. And we started talking especially to Ignacio and to Alejandro González Tudela about what to do. I wanted to do something different than the Hubbard model, because if you hear talks about quantum simulations, and in the end everybody is talking about the Hubbard model, that's a bit, not enough. But it turns out, if you want to do something new, it's not that easy. So why would we want to do this? So this is going to be a quantum simulator for strongly coupled emitters. Why? Well, because otherwise it's hard to get to. And the physics is as follows. So if you have two atoms, or two quantum emitters in general, and let's say they're spaced by distance d, which is larger or comparable to the optical wavelength at which they radiate, then everybody knows it's a fundamental assumption of almost all of quantum optics that they're almost independent. You don't have to worry about it. But as soon as this distance here becomes much smaller than the optical wavelength, they cannot, right? I mean, there's an atom sitting here and wants to radiate a photon. It knows that there's something else sitting next to it that may absorb it. So you can enter the regime of strongly coupled emitters, which is where a lot of interesting physics lies. And many people are interested in getting there and have started over the last 20 years already to design experiments on where one can try to put quantum emitters, in this case it will be atoms in an optical trap, close to interesting nanophotonic structures. Right? And to do this, though, you realize very quickly that you have to put these atoms extremely close, let's say lambda over 10. If that's an optical wavelength, you're already at something like 50 nanometers. And controlling things optically below the diffraction limit is extremely challenging, which is why these experiments, they're starting to work, but it's very hard. And unfortunately also, of course, the coupling of your emitter to vacuum is just given by the natural lifetime of your emitter, or natural lifetime of the atom. Right? You can engineer any interesting vacua you like, and that's the role of these nanophotonic structures here. But the tuning capabilities and the things that you can do are rather limited. Now, the simple idea of a quantum simulator is let's replace things by atoms and see if we can make things easier. And the trick is that this idea by Ignacio's group is to replace this optical wavelength that is very short with the de Broglie wavelength of a tunneling atom that can be made much longer, and that be many micrometers long. And then one has space enough to build an experiment that allows you to play with this kind of physics. I'm going to show you a mapping where then this coupling to vacuum can also be done by a simple Rabi frequency and detuning, simply be laser controlled, and the interesting vacua can be engineered by engineering band structures and an optical lattice. So the nice thing about that is that it's very flexible, and that can be very clean. Now what do you need? You need some sort of mapping, and the emitter is going to be represented by a combination that looks as follows. So imagine you have a two-level system in an atom, in this case the ground state of strontium, for example, and this excited clock state. And let's say that you can make a very strongly state-dependent optical lattice. Looks like so. Then you can place atoms in those traps in different states, and you can see that because this here is so shallow, this atom can move relatively freely, while this atom is tightly trapped and cannot move very much. The other capability that you need is that you need to be able to shine laser beams at this optical lattice in a site-resolved way. So you need to be able to focus very tightly using a microscope, a laser beam onto individual lattice sites. That's something the Bloch group is very good at. If you can do this, then you can engineer situations like this, where, say, this side is coupled and this side is coupled, but the other ones aren't. And then this here is supposed to represent free space. So there's nothing going on here. While down here, if the atom is in the ground state that can move freely, that's supposed to represent the traveling photon. And the relevant wavelength here, again, is the de Broglie wavelength of this tunneling atom. This here looks like an emitter in the ground state, because imagine this atom moves over here. It can be actually absorbed by the local coupling and be trapped in this upper state where it can't move around freely. So that looks like a box that can absorb a photon, whereas this looks like a box that can emit a photon, right? That atom could be promoted down here and can start to tunnel away. So that's the very simple idea that was promoted by Ignacio's group in many papers over the last decade or so. And it's a very intriguing idea, and I'll try to convince you that it's easy to write down, but a bit harder to get to. So let's see. Why is this good? It's good because the simulation that one can then do has all these parameters here. It has the tunneling matrix element of this moving photon here that can be widely tuned, very well controlled. This local coupling, if you can do it, is parameterized by Rabi frequency and detuning, which are perfectly well controlled. And everything is tunable. And the interesting thing is now, because if you have a laser that is good enough, you see now this lattice structure here resolved in quasi-momentum. The upper state has very flat bands, the ground state does not. And that means you can now locally actually shine in laser beams in momentum space and couple these excited state emitters to any point you like in the band structure of the lower band. It could be at the band edge, could be at the band center, or somewhere else. And depending on what you do, you can have realize different couplings to vacuum, get different types of physics. And that's, I think, very attractive. Right? It's a very attractive package. So how do you do this? Now comes the story of how to actually get there. The first thing you saw is that you need these very strongly state-dependent lattices. And how does that come about? So just to remind everybody, if you trap atoms with laser beams, they're trapped based on the AC Stark effect, and the AC Stark effect per se is, of course, state-dependent, right? If I have a ground state atom, in principle, will be trapped differently than a not ground state atom. That's what you see here, represented by the polarizability of these two clock states versus the trap laser wavelength, and you see how it changes. And if you're very lucky, you can find a particular wavelength where these polarizabilities cross. That's very important, because then these traps look the same. If you're over here, this looks very different. And doing good optical spectroscopy requires this situation here, which is why it's called a magic wavelength lattice. It's called magic again because the invention of this caused all the optical clocks to start working, because all the problems go away and finally you can get something to go. This was very, very important development here in the early 2000s. And if you have this, if you operate at the magic wavelength, the reason why it works well is because then the internal states of the atom decouple very well from the motional states of the atom. In an ion trap, you have this for free. In an atom, you don't. And then you can have many of these atoms at the same time, and you can do experiments with very good signal to noise. And that's why everybody who worked with strontium only ever worked at this so-called red magic wavelength here at 813 nanometers, because you can't do anything else anywhere else. But for quantum simulations, it was actually interesting to look somewhere else. There are other scenarios, like I said, where you want these very strongly state-dependent lattices for a simulator that are not what you want for a clock. And there are many interesting scenarios here. So for example, you can find this red magic wavelength, both traps look alike. You can find blue magic wavelengths where they also look alike, but they're repulsive. Or you can find situations where the traps look exactly opposite. Personally, I think these are the coolest, where there's two wavelengths in strontium in particular, where the ground state can be trapped, the excited state sees nothing, and the opposite. And the good thing about strontium is, you see this here, is that they end up being at wavelengths that are reasonable. So reasonable meaning visible. And that reasonable meaning in combination with microscopy. So you have a chance of using these wavelengths in combination with a microscope and regular optics to play with atoms. And that was very exciting for us. So we first started to look into this as a first step towards reaching our goals, and came up with a trick with which we could measure that very precisely. Be happy to go into more details, but in the interest of time, I'll just show you the result. We were able to find this wavelengths where the ground state sees no potential at all, and the excited state is nicely trapped, with a very high precision. Because we have trapped particles using modulation tricks, you can measure this really well. And what we showed is that we can get 46 dB, so almost 5 order of magnitude suppression of the potential of one state with respect to the other. When people talk about state-dependent lattices in alkaline metal atoms, they talk about levels of a few percent, maybe 10% or so. So this is qualitatively very different. And it's only possible because of these special features of this atom. So we were very happy. This allowed us to measure all kinds of properties of the atom that were previously unknown, and that worked really well. So that's the first building block. Second building block that we want for this quantum simulation, I showed you that we are interested in having these atoms in the ground state tunnel around freely with a long de Broglie wavelength. And if your systems are small, that's not good, because then the atom will tunnel to the edge of the system and be reflected, and you see edge effects. And for the types of things that we're interested here, namely these freely flying photons, that's really no good. So the next thing that we had to get to is to get to much larger systems, and show you how to do that. So there's just as a comparison, if we talk about state-of-the-art quantum simulators for fermionic atoms, it's what I set up in Harvard before I joined, they look sort of like that. You have in the end maybe 30 by 30 atoms or so at temperatures of maybe half the bandwidth. That's very much state-of-the-art. So you see this regular filled array in an optical lattice. There's a few defects, but works quite well. The next step then was to make that even colder, because this is clearly not quite cold enough for the interesting quantum simulations that one would like to do of the Hubbard model. And one of the tricks was to say, let's take the system, split it into two. Let's define an inner system that I care about, that I want to make very cold, and let's define an outer system I don't care about, and let's use that outer system as a fridge. So the idea would be to transfer the entropy from the inside here to the outside, and then throw away this red region, and then you're left with a much colder system. So this was, with a colder system. So this was the only way that, for the first time, antiferromagnetic correlations in these Hubbard systems could be shown, and you see the reduction in temperature is about a factor of 2, but you have to sacrifice about an order of magnitude in atom number, which is why, in the very end, state-of-the-art Fermi Hubbard systems, they're kind of small, so they look like that. Now, why is that so? That's so because optical lattices are built from laser beams, and a laser beam does not have infinite size, so make your laser beam yay big, then there will be a potential variation across the beam. If you make it bigger, you have to have quadratically more power. So if you then do the math, then you end up with very roughly these systems for realistic laser powers that you can buy. And that's not really improved over the years. It sounds like a technical limit, but it really is a bit more than that. Typically, the way these things are built is you take this laser beam, you shoot it through your vacuum cell that's sketched here. There's a microscope sketched on top that looks at your sample, and then the laser beam is retroreflected from a mirror. So that's how you make an optical lattice. Now, our idea was very stupid, is to say, well, if that's a problem, why not reflect it not just once, but many times, and build an optical cavity. But what we wanted to do this sort of thing here was an optical cavity that supports at least 2 dimensions. And it should have a rather large waist and support large laser beams. But still, you want this to be a stable resonator that you can stabilize your laser beams to. It also needs to be XHV, extreme high vacuum compatible, to do any of this. But the upshot is we were able to do this, and we're now getting lattice mode volumes about a millimeter cubed. So there's a millimeter cubed filled with optical lattice, and I'll show you in a bit that the mod insulators that one, based on our potential measurements that one could make with this setup, are significantly larger. That wasn't easy. If you want to do anything new, tends to cost some work, because otherwise people would have done it already. Engineering this thing, which has no moving parts, there's no glue here, this is all glass, optically contacted together, was the PhD thesis of Andre, and took the combined work of quite a few people that we worked with over the years. We're really quite happy with it now, because we think it has quite a few other applications as well, and we're really thinking that this is a way forward for neutral atom quantum science. Now, As a first proof of principle, then we put this in vacuum, sweep a lot of things under the rug here, and started loading some atoms into it. So you see here this cavity, 2 laser beams that cross. There's an optical lattice forming here. And we intentionally now made this cavity lattice at a wavelength where, again, it's not this magic wavelength, but where the potential looks different. And if you do this, here's a sample that we load. Depending on the detuning that you use for the spectroscopy beam that we shine in, you can actually shoot holes in the sample. It's kind of cool. So you can see either make a hole in the center or you can make these rings. And that's just, again, because the Stark shift here is large enough and the laser is good enough that we can spatially resolve the excitation. Then we can do a normalization trick to just make it look a bit more pretty, and we can create these rings. If you then, it's a bit hard to see, take a lot of these images here and stack them up vertically as a function of detuning, you see this very nice paraboloid. I hope you can see it a bit. And that's a direct image of the envelope of this potential here. So we directly spectroscopically measure that with very high precision. In principle, you can actually do this pixel by pixel, which is what we then did. Pixel by pixel, you can find a resonance. And so on every pixel of your image, you know how deep the potential is. In principle, if your microscope is good enough, that means you can, in principle, do this for every lattice site. You can create a map of these resonances, and then from that extract how big a Mott insulator would be if you put it in this optical lattice. That's where this figure comes from, that I showed earlier. Also, it allowed us to calibrate the wastes, so it all works out. In the end, we have about 60,000 lattice sites here. Similar to what Christian showed, you can also look a bit more. You can look for sidebands, and you can see even more rings. And that's kind of cool because that gives you access to also not only sidebands, but because this lattice is non-magic, you see different carrier transitions for different motional states in the lattice here. This directly gives you access on a per site basis to the population in the optical lattice, meaning also temperature measurements locally, and we can directly measure that. That was very important to us. We then showed that from watching how this evolves over time, you can also see the lifetime in your trap, heating rates and things like that. We were very happy that we could show that there's basically no disadvantage of this new cavity lattice based on the conventional free space lattice that everybody uses. Okay, since I just got the signal, got to speed up a bit. Now the next step for a quantum gas microscope, which is what we're building. So we're building this 2D lattice system. We need a microscope on top so that we can, in the end, address individual lattice sites with this clock laser beam, is to prepare a single layer. Right? You have a microscope. You start with a vertical lattice maybe that has these pancakes here, but really you would like to focus your microscope optic on one of those and not have atoms in these other layers present at all. Typical way to do this is to apply a strong magnetic field gradient and then kill all the other optical lattice layers by shooting out the atoms. And if you do that, then this is sort of an example image from when we did this at Harvard. Then you see images like that. So that's the first step towards having a quantum gas microscope where you can look at individual atoms in a lattice. And strontium turns out to be not so easy. Okay, I'll skip this. Basically, there's only one transition that's narrow enough and magnetic field tunable enough to do it. But it's a weird transition. It's a magnetic quadrupole transition, which I had no intuition for. So we first had to learn a bit how to work with that. So we did that. There are interesting selection rules here. So if you write this down, the level scheme of a j equals 0 to j equals 2 transition, what are the selection rules? I have no idea. So here's an experiment. So what you see is that as a function of tuning the quantization axis angle, the B field angle here, and as a function of looking at the population in these states, you see different spectra. They become more or less wide. That's maybe the first thing you see, and that's because in addition to having these selection rules here, also again the lattice becomes more or less magic, more or less matched for both states, depending on how the quantization axis is tuned with respect to the optical lattice. So that's one thing. And you also see that, well, at 0 degrees, it basically looks like a regular dipole transition, right? But as soon as you start tuning here, you see that I have no intuition for why this works. So we think we now understand it, and what the nice thing is you can see at certain angles here, for instance this one, how the lines become extremely narrow. So we can get both. We can by playing with a magnetic field, or alternatively the lattice polarization, we can excite what we want even on this weird quadrupole transition. So here we did this systematically by playing with the polarization of the optical lattice. We can even find now a position where for this quadrupole transition, for a particular magnetic sublevel, the lattice is extremely well matched and it just works. And this is a neat trick that works for most transitions. It doesn't work for the optical clock transitions, but for most transitions it does. So this gives us a new knob to play with atoms. I think, Andrea, I'll be done. Okay, so why did we do this? We want to throw out all these other layers, right? So that's what we want to do, this experiment. But that was a bit too hard to start with, so we tried to do the inverse thing and kill a particular layer of atoms that we cared about. That's what we did here. So we shot some light in, removed some atoms, and then looked again. And you can see here a hole that we were able to burn into the atomic distribution in the presence of this magnetic field gradient that's consistent with killing atoms in a single lattice site. So that's the status as of maybe 2 months ago. And right now, Dimitri, who's here in the audience, is setting up the microscope. This was just a proof of principle experiment, and they're working quite hard right now on getting the microscope working. So we're very excited that very soon we hope to have the first quantum gas microscope worldwide for strontium atoms. Okay. Showed that we can make very highly differential optical lattices, which are a new tool for quantum simulation and potentially other things. We were able to scale up optical lattices by 2 orders of magnitude at least, and we've now made a new type of transition work with the things that we needed to do. Once we have this, we're ready to do this quantum simulator. Again, the atoms will sit in this optical lattice here, which is very flat, and using a microscope, we will then be able to define these individual optical tweezers that locally can drive the clock transition. Once we have that, there's many things we can do. Even the single body physics is kind of interesting because we're sitting in 2 dimensions and we can directly image the atomic distribution in the cloud, which is different than what people have been able to do before. There's a pioneering experiment in one dimension, but without spatial resolution by Dominique Schneble's group. So basically by doing what they did again, we have completely different access to even the one-body physics, which involves seeing photonic bound states, being able to engineer the directionality of the emission, and looking at Markovian and non-Markovian dynamics depending on where in the band you couple to. This was this thing about coupling outside of the band versus inside of the band. Once we have more than one atom, which is really not that hard for us, then you can look at the excited state manifolds of the Dicke Hamiltonian, right? Because this is very hard to do typically in a real life experiment, because putting more than one excitation in there is hard for us. It just means adding one more atom. Once you can do this, and if you can also play with the phases of these excitation beams here, such that you can create superpositions between these different emitters, you can engineer very good symmetry protected subradiant states which live longer than they should, based on single body physics. And longer term, there's many new ideas, mostly by these guys, on we have atoms available with bosonic statistics that don't interact. We have atoms available with bosonic statistics that do strongly interact, and we have fermions that interact. So you could think of very new things like looking at the physics of interacting fermionic baths, which is beyond, of course, looking at nanophotonics, and of course also very long-range interactions. Okay, I think I'm almost done. Give me 15 seconds. So my point here was that being able to, well, we have to actually do new quantum technologies to do new things, but if you do it, that's really, I think, the motor that drives all these new developments in the field. And we're looking very much forward to the next few months where we think we can have very new things. Here's the team. Of course, I'm not doing this myself. Jan did a lot of the work on triplet P2 spectroscopy. Valentin and Dimitri are currently setting up the final microscope. There's many people who have helped over the years, and of course, this all happens in Emanuel's group. And with that, I'd like to thank you for your attention, and I think we have time for questions.
Thank you, Sebastian, for the beautiful presentation and results. There is time for 1 or 2 short questions. We are slightly over time. So maybe I ask myself a question. So what is the intuition? If I understand now you make an effort to make the lattice very homogeneous as much as possible, but what about if you then add disorder or other potentials? Is there any physical intuition where you can couple the simulation of quantum electrodynamics to this extra knob that is available in the cold atoms?
Oh, I'm sure you can do something there, but I think the disorder comes for free. I think this typically is something that we fight against. So I try to make it as good as possible first, and then maybe one can add some control disorder, like something spatially modulated or so. I think that would be very interesting.
Okay, if there are no other questions, I would like to thank Sebastian again, and we then move to the next session.
Thank you.